Good evening, ladies and gentlemen. Let's start our fourth last session. Rafael Maman, partner, cyber strategy, cybersecurity, PricewaterhouseCoopers. The floor is yours.
Good afternoon, everybody. My name is Rafael Maman. I'm leading the Global Cybersecurity Center of Excellence of PwC for OT security and critical infrastructure protection that is based in Israel. We are going to talk today on how we ensure cybersecurity for critical infrastructures, but I think we can't really start talking about that without first saying something about OT security. I'm sure that if I asked you what is IT, you would all know the answer. You know, the internet websites, email servers, ERP systems, CRM systems, whatever makes the modern corporation work, we all know that. But what if I asked you what is OT? I think that some would not. So let's fix this. OT, operational technology, comprises the industrial control system and the non-industrial control systems that run and operate all our factories, our manufacturing facilities, the lifts in this building, indeed almost all of our national critical infrastructure, oil and gas, nuclear facilities, water facilities, power plants, all are operated by operational technology. It is here where the internet literally touches the physical and kinetic world that we see a risk equation of a totally different order. We don't talk only about risk to data privacy or risk to intellectual property theft. Here in the cyber kinetic world, we talk about real risk to human life, risk of disruption of critical operation, risk of environmental disasters. So, despite this very high risk equation, OT security has been out of focus in the cybersecurity world for a long time, whereas IT security was here around for as long as we can remember, for the last 15, even more years. And throughout this presentation, we'll also understand why. But in the last few years, this is changing. And we see that focus is shifting from IT to OT across the board. The good guys, the bad guys, and what I call the real ugly guys. And those are nation states that discovered that cyber attacking industrial control systems is a weapon, is a very high precision weapon that can be used for that purpose, and actually started attempting using it in this way. As a result of that shift from IT to OT, we also see that governments and industrial enterprise, again, all over the world, take notice of that and start taking proactive action through regulation, through enforcement, through awareness. But you see really all over the world clear focus of governments on protecting their national critical infrastructure after understanding the risk equation. And this is why I am predicting that the most significant impact in cybersecurity in the coming years is going to be exactly here in protecting national critical infrastructure and industrial enterprise. Now you would ask yourself, you probably are asking yourself, why with such a high risk this has been taking us so long in order to put our focus on it. And it is certainly not because of what you usually hear from many, that industrial control systems are isolated from the internet and therefore protected. This is simply not true. And you'll see that. You'll see that in the test case that we're going to run together. So it's not because of isolation of the industrial control systems, and it's also not because of lack of incidents. This is an attempt to capture what I would call iconic or well-publicized attacks, cyberkinetic attacks and incidents over the last 40 years. And you can see that back in 1982, There was an attack on the Siberian natural gas pipeline, which it was never proven, but by many considered to be the first proven cyberkinetic attack ever. And since 1982 and until today, there have been many events and incidents in the cyberkinetic world that happen continuously, and still focus has not shifted. And again, the question is why? And the answer is simple. It is because it is hard. It is very hard. It's hard to master the industrial control systems in order to attack them effectively, and it is very hard to protect industrial control systems. And for that purpose, we preferred not to deal with it as long as we didn't have to. But then things changed. 10 years ago, a well-publicized cyber attack on a nuclear enrichment facility in Natanz in Iran managed to cripple a nuclear enrichment facility from a distance with a keyboard without any human involvement. As a matter of fact, 1,000 centrifuges were destroyed remotely, and that was a sign for everybody that with industrial control system cyber attack, you have a super-grade weapon. After the Stuxnet event, that was the code name of the attack on the enrichment facility in Iran, followed an attack in 2014, right, on a steel mill in Germany, and then in 2015 and 16, 2 attacks on the power grid in the Ukraine, and then in 2017, an attack codenamed Triton that we will actually use as our case study later on a chemical plant of Saudi Aramco and Dow Chemicals in Sadara in Saudi Arabia. And all these events prove the point that cyber attack on industrial control system is a cyber weapon, can be used as such, and we should protect ourselves against it. What I want to do next is to do a sort of a thought experiment together with you. I usually do that in focused workshops, and admittedly, it is the first time with such a large audience. But I want to take you through a case of a cyber attack on an industrial control system from start to end. And I think that you would then realize first how hard it is, but also what are the risks and what could be the devastating results of it. The attack we're going to talk about happened in 2017. But the attackers, or the hackers, started it 3 years earlier in 2014. And for 3 years, they've been in the corporate IT systems persistently and continuously. And that should tell you something about the scale, about the funding, about the organizational power that is required in order to put together such a sophisticated attack. 3 years of work of a team of top hackers. You can calculate yourself the cost and the effort to orchestrate it. Now, what they did, for the first year, the hackers did nothing more, and what I'm telling you now is based on open source forensic reports of the attack. For the first year, they did nothing more than to move laterally in the corporate IT network, to maintain persistence in the network, to do reconnaissance, to collect intelligence, to look for an entry point into the industrial control systems, nothing more. Then in 2015-16, the hackers managed to get an entry point into the industrial control systems. They did that using 2 methods. One, through a poorly configured firewall. The second one, through a vulnerability or a flaw in the Microsoft Windows operating systems. At the end of that process, they managed to enter from the IT system into the industrial control system, into the SCADA network. And the very first thing that they looked at or tried to enter when they were in the industrial control system was the distributed control system, the DCS. Not sure how many of you are familiar with chemical plants or oil facilities or nuclear facilities. The DCS is the heart and the brain of operating the plant. It is where you have all the information you need about the hardware, the controllers, the sensors, everything you need. And it is this system, which is controlled from the control room, that controls and monitors the entire plant. Once you are in it, you know everything you need to know about the hardware of the plant. Having breached the industrial control system and compromised the system, the next thing that the hackers did was to study the information that they could glean out of the DCS, and they figured that the system they were after, something that is going to repeat frequently in the next few minutes, a system called Safety Instrumented System, or SIS. They figured that the system that is used in that plant is a system of Schneider Electric, an American manufacturer. They also got the model, the firmware model, the version, everything they needed to know about it, and most probably then went on and purchased exactly the same system and exactly the same model and exactly the same firmware model, and used that hardware in order to develop and to test the malware that they were developing. In the process, they also discovered what is called a zero-day vulnerability in the Triconex. Triconex is the name of the Schneider Electric system. A zero-day, you all know, vulnerability that has not been reported and therefore not been fixed or patched. They discovered it in their experiments and used this in order to enter from the industrial control system into the SIS, into the safety instrumented system. You can follow the flow of what we call attack vector on the left side. So now that the hackers were inside the SIS with a direct reach of the safety controller, really all they need to do was to deploy the malware into the system, and that malware, codenamed Triton or Trisys, depending on where you read it, was indeed deployed into the safety instrumented system, and the function of it was to disable it. You should figure out what it means. It means that the safety instrumented system is such a hardware that at the moment there is any emergency safety situation, it should come to life. So if there is high pressure, it should do something about it. It should sound an alarm. It should, spray water. The moment you disable it, all you need to do is really sit and wait. Wait for a safety emergency situation to occur, and the rest will happen by itself, devastatingly as that can be. In June 2017, there was a bug in the code of the hackers, and that led to the system, the SIS, moving it to what is called in engineering term fail-safe mode. And after that, there was a shutdown in the plant, and the operators of the plant dismissed it as a non-event, a malfunction. And then 2 months later, in August, again, a bug in the code, a few systems tripped, and caused another shutdown. But throughout all that period, there was no safety emergency situation. So really, there was no damage done other than shutting down the plant. On March 23rd, an emergency situation, safety situation did occur. A pressure was building up in the system, and fluid was filling up the pipeline that is going into the safety valves and into the condenser. And because of that, the pressure at some point, I'm using some engineering terms, that's fine. At some point, the pressure reached a point that is called the blowdown. And when it reached that point, some 200,000 liters of heated raffinate moved and were disposed into the collection header, the collection drum. Again, I'm sure that most of you won't know the engineering details. This is not a common event in chemical or oil plants, but it can happen. And by itself, it's not an event that cannot be contained. And it's not an event that should lead to a disaster. The day operator, that is the panel operator sitting in a control room, noticed the spike in pressure and mistakenly keyed in a wrong control command. And here is the point. The very first thing that happened is that the DCS, the distributed control system, remember we talked about it early on, the brain of the plant, issued an automated scenario that was not foreseen by the designer of the system, not foreseen because it was not the designers of the system that were now controlling the DCS. Immediately after, the safety sensors did not work, of course, but it is controlled by the safety instrumented system, and alarms were not heard. You know, when the blowdown pressure is reached and fluid is going down to the collection drum, there is an alarm that should be heard. There was no alarm heard because the SIS was not functioning. And then because of that, a cloud of vapor started moving across the facility, over the pipe rack, and into the trailer area. That's where the contractors were staying. And again, in the facility, there should have been a sensor that sensed the vapor cloud moving and sound an alarm. No alarm was sound. The safety instrumented system did not respond. And so the vapor cloud reached the trailer area and was ignited by a backfire from a truck that was idling nearby, causing a massive explosion. And then from the explosion, the pressure wave moved across the facility and several miles further, hit the contractor trailers, killed 15 people on the spot, and severely injured 180. Now, there is nothing in the story I told you that is not accurate. The only thing is, that the only reason that you didn't read about it in the newspapers is because I conveniently linked together two separate events, unrelated. But the match is 100%. The first event really happened. That's the Triton event in Saudi Arabia, the attack on the facility of Saudi Aramco and Dow Chemicals. And all the first 4 steps of the attack vector happened as I described. Luckily, after the second time that the system moved into a fail-safe mode, the operators took notice, started suspecting that something is wrong, and after that investigated, found the malware, removed it, and luckily nothing happened, and the event ended. The second part happened in 2005 in a BP refinery in Texas City in the US. Again, all the 3 steps I described are correct. The data in the accident report prove that the 2 components that were the cause of the accident were indeed the failure of the DCS and the issuing of a wrong emergency scenario, and the fact that the safety instrumented system did not respond, did not sound the alarms, did not activate the sensors. So the 2 touch points that were tampered with by the hackers in Saudi Arabia were exactly those 2 that caused the devastating accident in Texas City in the US. And now that you know that, it wouldn't take much imagination to realize that we could have had all 7 steps in the case study we went through happening in one location. And if that would have happened, then those pictures would have come from Saudi Arabia and not from Texas City in the US. Which brings to mind something else. In April 1942, as the Americans were mobilizing to the Pacific Theater, Admiral Yamamoto, who is the architect of the Pearl Harbor attack, wrote in a letter just a few months after Pearl Harbor, and I'm quoting, "The first stage of operations was kind of children's hour. Now comes the adult's hour." Ladies and gentlemen, make no mistakes. The cyber threats we are seeing to our industrial control systems, to our critical infrastructures, are the adult's hour of cybersecurity. And if we are not prepared, then they may make the threats that we are seeing in our IT environment look like children's hour. So what do we do in order to be protected? Well, first we do whatever we know what to do, and those things I like to call the known solutions. What I claim is that this is not enough. Not enough to do what we know that we need to do, to separate networks, to put diode single-way connections. All those would not be the solution. Those are just must-do, and those are known solutions. What you have here is an end-to-end framework for national critical infrastructure protection. This is the framework that we're using in PwC, but there are other frameworks that are not going to be a hell of a lot different. It starts with assessing the maturity of your critical infrastructure facilities, goes to having a cyber strategy for protecting critical infrastructure at a national level, developing and executing regulation for industrial control systems, having a national CERT and possibly sectorial SOCs, hybrid SOCs, going down to the level of operations in the critical infrastructure. We need to implement monitoring and detection technology on the SCADA and ICS networks. And the last item you are not going to see in other frameworks, having a laboratory environment to test technology before you put it into the plant. Now, for each one of those 6 components, I can, and I don't have time to do that now, but you need to believe me, you can split them into known solutions and what I like to call the known unknowns. Those are elements that we know that there is no one clear solution, and this is the known unknowns that I think you should pay attention to, because I am convinced that you or your colleagues are taking care of all the known knowns. I'm going to talk through 2 of those examples. I'll take example of known unknowns in the area of regulation, and then one in the area of national cyber labs for ICS and OT. Let's start with regulation. I need to say that counter to my nature, I actually think that regulation is essential in the area of protecting national critical infrastructure. We need to put in place sound regulation. But what is sound regulation? If we look across all the standards and policies around the world, you're going to see that they are mostly divided into 2 groups. There is one group of regulations that are generic. They work for any critical infrastructure facility, any sector, and then there are those that are very specific for a sector or even down to a segment in a sector. Let's do a quick run, take the world east to west. If we look at the east, we see that there are just examples. Very good standards, one in Japan, one in Qatar, that are of the generic broad spectrum standards. And then we see one in South Korea that is going down to the level of defining a policy for diodic or one-directional communication link from the industrial control system to the outside world. We go further to Europe. Again, you see generic standards like the one that ENISA supports. But then we also see a list of very specific sector-specific standards, one for the aviation industry, one for the nuclear industry, one for the railway transportation. And then the US, really a source of many very good standards and policies. We see generic standards like the NERC CIP or the NIST framework for improving critical infrastructure cybersecurity. You all know those, but there are also very specific standards and policies, for example, for the nuclear power plants or for offshore oil and gas facilities. Let's zoom in for a second, just in Europe, because we are in Europe. So in the EU, there are 3 standards. If you now do a survey across all critical infrastructure operators in the EU, you'll end up with them using one or a combination of these 3 standards. The IEC 62443, I'm sure you're aware of it, is looking at the problem from a position of addressing the point of building or designing cybersecurity into the industrial control system itself. So it's looking at the core of the industrial control system. And it is a generic standard that works across industries, across sectors, and across systems. The American standard, the NIST framework, Also very popular in the EU, especially in companies that operate both in the EU and in North America. Again, looking at the problem from a different angle, this is a risk management angle. So what the NIST framework is doing, it's a collection of best practices and examples and policies from across the industry of things that work well, and then putting them together in a risk management framework that is really useful, and useful in the US as well as in Europe. And finally, the ISO 27001, very popular in the EU, sure you know, is looking at the problem from a management system perspective. The standard, already 6 years in operation, is looking into setting up an information security risk management, management system. So again, 3 standards, one looking at management, one looking at risk, one looking at building it into the industrial control system itself. So what is the known unknown? It is my conclusion that if you just take any standard and use your regulation based on that standard, it's not going to work. You know, those standards are very specific, developed in specific countries for specific cases. So if you just say, I'm taking the NIST and using that as a base for my regulation in a country X, in Russia, for example, this is not going to work. So the big question is, can we really craft or really handcraft out of all these myriad of standards and policies a regulation that can be effective and can allow us to regulate effectively? And my answer is yes. And I'm basing it on the experience that we have in Israel, where the regulation for private critical infrastructure was done by taking relevant standards from all over the world and then handpicking those parts that are relevant and creating a lean regulation, lean in the sense that it can be implemented across the critical infrastructure sector and can be accepted by the critical infrastructure operators, and it works. So it is possible, it's not easy, but that known unknown will soon become a known known. And the second that I want to leave you with is something you won't see often. I call that barriers for improving cybersecurity in critical infrastructures. And those are 2 types of barriers. And those of you that are in the business of critical infrastructure would recognize them. The first one is what I call a trust barrier. You know, people dealing with critical infrastructure are engineers, technicians, system people. Those are by definition distrusting bunch. They don't trust anything unless they play with it, they tear it apart, they test it, they connect it, they need to touch things. So there is a trust barrier between them and the technology providers. You show me one plant manager that will allow you to put cybersecurity technology in a running plant, in a running refinery or chemical plant, and I will show you the first one I've ever seen in my life. They don't exist. Then there is a trust barrier between the technology providers and the regulators, and then a trust barrier between the regulator and the critical infrastructure operators, and we need to solve it somehow. And second is a barrier for budgets. Improving critical infrastructure protection requires major investment, and the people that make investment decisions don't know much about the industrial control environment and never experienced how it works. So it's very hard for them to make funding and budget decisions in this area. In other words, we are really talking about an intersection of business, technology, and experience. Coincidentally, also a method that PwC is using in our consulting, and it's hard to solve. Can we? The answer again is yes. And again, I'm using here an example from Israel. The Ministry of Energy, together with the Israeli National Cyber Directorate, saw the problems of the barriers for entry, saw the trust issues, and had a vision to develop a national cyber lab for industrial control system and let all the players, the critical infrastructure operators, the academia, government, technology providers, test technology, test it in a real-life environment before they put it into use in the field. Now, because PwC won the tender to design, develop, and operate this lab, I can show you simulations that we did of kinetic modules from that lab. In that case, you see oil and gas facility, water desalination plant. There are more, and they are all real kinetic modules operating on top of SCADA and full PLC systems, allowing people to go and test any technology, remove the trust barrier, be sure about the costing before they put it into the plant. Now, this is still what I call an unknown, because I don't know of any other example, but I'm sure that based on such example, you'll see national cyber labs for industrial control systems and operational technology coming up as indeed the sixth component of an end-to-end framework for critical infrastructure protection. Well, just on time. I hope that through this presentation you learn a little about the risk, about the complexity, and about how difficult it is both to attack and to defend critical infrastructure facilities. And I hope that you are a little better prepared for the adult's hour of cybersecurity. Thank you very much for your attention. I didn't say, but if there are any questions, this is the last session, so we have all the time we need. If there are any questions, I'll be happy to.
Ladies and gentlemen, please, you can ask questions. This is a hot topic indeed.
Thank you very much.